Chuck. So lesson 9, and I promise you to talk about time, but you'll have to wait a little bit of time because I got a certain number of questions. So to answer these questions, because I realized that from the questions that there were holes here and there, so I want to answer. One is sort of historical, two are very technical, and then there's another one about something missing about the interpretation, which I said. So let me list the questions so I don't forget. The first is a relation with Penrose spin networks. What does Penrose spin network have to do with these spin networks? And in particular, in Penrose spin network theory, there is something called the evaluation of a spin network. So what is the evaluation? It's a number. Evaluation of a spin network. That's the first question. The second question was, I wrote at some point this metric in the Hilbert space of representation J, and I said, somebody told me, well, you said I'm going to say later what it is and give the exact formula, which I didn't, so I'm going to give you this. That will be a filling thing. And somebody asked me the relation with the Clebsch-Gordan coefficient that one study in elementary quantum mechanics between the intertwiners and the Clebsch-Gordan coefficients. And basically they're the same thing. And I want to just put the dot on the i's and say what exactly. So Clebsch-Gordan coefficients are the things that allow you to take two particles, spin J1, J2 with angular momentum M1, M2, and decompose it into the composite system into representation J with angular momentum M. And what is the relation between these and the intertwiners? These are the three main questions. And then, just rapidly, what fixes the number? I said that the EI, the E vector, is some number. H bar G, the operator. So what is this number? And somebody said, what about the other operators, the diagonal operators? F of H, HL, put an L also here. What is their exact interpretation? I sort of waved my hand saying, well, when you go from one reference to the other, you rotate, but that was not very precise. In fact, strictly speaking, not correct. There's a missing piece. So I'll just say something rapidly, even if we'll go back to that. So let me go through these questions rapidly. First, Penrose developed a theory which he called spin network theory very early. I don't remember when, in the 60s or something like that. And he had some notes that circulated about that. It's a very pretty thing mathematically, completely independently of everything I told you. And when the spin networks through quantum gravity were not found knowing about spin network theory. In fact, we stumbled upon spin network, Penrose spin networks. In the process of diagonalizing the area and the volume, in fact, in the calculation of the eigenvalue of the volume, we realized that, in fact, it was Lee Smalling that at some point said, but this looks very much like Penrose spin networks. I didn't know about Penrose spin networks. Lee was in Verona, in Italy. We were sort of trying to diagonalize the volume and define this operator cleanly and do that. And the construction of the theory went through some very many turns, so I may say something about that. So there was not this clarity about the SU2 representation theory which we have now. In fact, we didn't even realize that we were doing SU2 representation theory. We were basically worked only in the fundamental representation, just, and putting together loops, and not realizing that putting together loops and symmetrizing them was essentially going to higher representations. So we have all this calculus, and it looked like something that Penrose called binary calculus, which is something similar to spinor calculus, but with some minus somewhere. And Lee said, but this just looks like spin network. So this was 94, something like that. And Lee Smalling and I were working in Verona. So since we were confused, we decided to call Roger Penrose. And Roger said, well, come here. And so Lee took an airplane from Verona to Oxford to have Roger Penrose explain him how you do calculations with this binary calculus and spinor calculus. We were confused by a minus sign horrendously, whether we had to symmetrize or anti-symmetrize these things. And so Lee was in Oxford, I was in Verona, I called him. I said, so what did Roger say? Do we have to do the symmetric part or the anti-symmetric part? And the answer was, oh, Roger says that this is the same, which, you know, put us in total black. And in fact, it is the same, just a matter of definition of where you put the minus. So it's this. So why did, what are Roger Penrose spin network and why he did that? Well, essentially, he was considering graph, trivalent graph, with spins attached to it, to each link. And he was saying that once you, this is a spin network. So a spin network is a graph, an abstract graph, trivalent, with spins attached to each link. And every time you have a closed one without external legs, you can get a number out of it. You can put a number. And the number is defined as follow. Essentially, you put an intertwiner. I use the language, this language, not the language that Penrose was using. You put an intertwiner here in each node. These are trivalent things, so you just get all this these intertwiners, things with 3 indices, many of them. You contract them, this leg with this leg, this leg with this leg, this leg. So you have all this contraction and you get a number. This number is the evaluation of the spin network. All right, so what? If you have some open legs instead of a closed one, you get 2 free indices, 2 indices in the representation of this final J1, J2 open links. And you have 2 vectors in 2 different representations. Imagine they are the same representation. Imagine they are in the vector representation. They're really vectors. Okay, and Roger noticed that they do behave like vectors, and proved a certain number of theorems, saying that with this structure, you can sort of reconstruct. I don't want to write the theorems and do all the, but from the structure you can basically reconstruct 3-dimensional geometry. So you can get 3-dimensional geometry more and more precisely by going with larger and larger J and bigger spin networks from just this this thing here in which you have only graph and half integers. Now, why all that? Well. Penrose explained this pretty clearly why he wanted to do that. In fact, in the text by Schrödinger, the 50s that I mentioned a couple of days ago, Penrose wrote an introduction. It's very nice. Because Schrödinger says, we were hoping to do quantum theory just as a continuous theory. I was hoping to do, Schrödinger says, but there is discontinuity, discreteness is unavoidable because there is measurement. So if you only look at the Schrödinger equation, you miss half of quantum mechanics, right? Which is measurement, eigenvalues. So discreteness is at the core. And the idea that space is discrete in the small, it's an idea that has inspired research in quantum gravity since the beginning. It's an old idea. And it's very simple. I mean, you take a particle, you squeeze it very small, because there's uncertainty principle, there's a lot of momentum, so there's a lot of energy. If there's a lot of energy, it has a lot of mass, so it makes a black hole around it, so it falls to the black hole. So there's no way to go smaller than something, and if you put the numbers, that's a Planck scale. So this idea is discrete as a Planck scale. So Roger Penrose in the 60s was saying, all right, so let's forget everything, and can I write a discrete version of three-dimensional space which has all the symmetries of three-dimensional space? And if you think it classically, it's obviously impossible, right? Because the moment you discretize, you break continuous symmetries. You cannot have something which is at the same time discrete. Symmetries are continuous. Where do you get continuity? But quantum mechanics is exactly what allows you to do that, because that's what, if you want, a representation theory of a rotation group. The group is continuous, but Lz has eigenvalues, and Ly also has eigenvalues, and L in that direction also has eigenvalues. So discrete in all directions, but in a funny way, in which when you rotate, the eigenvalue remains discrete, but you change continuously the probability of having one or the other one. Okay, so it's a funny way in which quantum mechanics is not a quantum mechanics, it's a complete discrete theory. It's a theory about discrete things in which continuity comes out in probabilities. So Roger says, wonderful. Since this is clear, can I just do space like that? Recover three-dimensional Euclidean space from something discrete in the quantum mechanical sense. I know how to do for a single vector, which is angular momentum. Angular momentum, but just one vector. Can I have the full space? So vectors here, vectors here, vectors here, vectors here. So I thought maybe I have a net of things, and that's how he invented, pulled out of the blue this structure. Then loop quantum gravity developed in a completely different manner, starting from general relativity. That's the actual history. Doing the canonical analysis of general relativity, started with Dirac, and then Bergman, and then Arnovit, Deser, Misner. It was a long way. And then there was this canonical form of general relativity. Ashoka rewrote the canonical general relativity in terms of new variables, which was the Ashoka connection and the E field, which is exactly this E field here. The E field is actually a two-form, and so you integrate on surfaces and you get these things here. The connection is the connection. We're going to come back to that. And at the beginning, the one was thinking of functions of this continuous field in space-time. So everything was living on a manifold. And the states on which loop quantum gravity was born, starting from a technical result by Ted Jacobson and Lee Smalling, that these were sort of solving the Will-DeWitt equation in some funny way, were states where a particular state, depending on a loop, which was the holonomy of the connection along the loop. So you had a loop in space, in three-dimensional space, embedded. And then we had operator on that. Lee and I had some operator defined on the space of these things, which are the grandfathers of the operator that I told you, of the operator L. We were called T operators, grasping operator at the time. And we realized that one can do a sort of geometry of that, but Jorge Pulling is the one who said you always get zero volume in this way. And Jurek Lewandowski is the one that realized that this loop have to necessarily, these states have to necessarily intersect. And so what really matters is the graph, not the loop. And we're very confused about this graph. This was a graph embedded in space. But of course, one of the key aspects of GR was diffeomorphism invariance. So this big Hilbert space, you have to divide by the action of diffeomorphism. And very soon, that's the beginning of loop quantum gravity, we realize that dividing by the action of diffeomorphism means to consider the graph irrespectively of where it is in the manifold. So that gave the idea of forget the manifold, just give the graph. Okay? And on this graph, there was this operator acting, and we had the operator for area and volume from the original operator defined here. So we were very happy. We did the first volume eigenvalue calculation. We published it. It was wrong because Renata Law realized it was a mistake, a minus sign in our paper. But then we did it right. And so finally we had this operator, and we realized that the graph with the operator of the eigen states were behaving exactly like the Rogers spin networks. Why? Because that's basically the only way of doing discrete three-dimensional space with the SU2 or SO3 symmetry, more or less. So that's the story. So I gave you a precise definition of what is the evaluation of spin network. How is it related to the spin network states? Right? We have a little bit more complicated structure. Let me put the graph here also to name the state. We have a graph with spin on the link, exactly like a spin network. But since the spin network can be more than trivalent, we have to say which intertwiner here. So we have this intertwiner on the nodes. So this is a state. But these are elements of an Hilbert space, which, for instance, in the basis of the group elements, we know exactly how to write down. This is a bunch of DJ MN of H, L, 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 L. Many of these contracted with all these intertwiners. So I can write this as a product over L contracted with a product of the intertwiner. And this contraction here, all the indices here and all the indices here are determined by the network. So each intertwiner has indices here, each link has indices here, and the network says how the, so let me put a gamma here. Good. So what is Penrose evaluation of the spin network is just contracting these without this. So if you put the identity here, you get a number. The value of the state, this is a state on HL, okay, labeled by all these things, gamma, J. The value of the state on the identity is Penrose spin network evaluation. So what is called evaluation of a spin network is the quantum gravity state of the spin network computed in the identity. That's a relation between Penrose evaluation of a spin network and the loop quantum gravity spin network states. So it's not the same thing. It's sort of they talk to one another enormously. They sit one into the other, but Penrose in Penrose theory, you have just graph with labels and a number you can compute out of it. Here you have graph with labels, each one of which give a function on SU2 to the L. Okay? It's clear the relation between these two things. Sometimes people are confused because, well, people come to me and say, oh, you have this spin network state, but it's just a number. How can it be a state? I mean, it depends on what. Something is missing.
To go from trivalent to four-valent, you just merge to...
Okay, so this is the next question. In fact, I'm getting to this. Since no, actually, I can do it now. A four-valent intertwiner can be thought as two three-valent intertwiners, and in some particular basis with a spin in between. So you say, well, also four-valent intertwiners are the same. Four-valent networks are the same as three-valent networks, and that's something you often hear. Well, careful, because if you have this spin network here with a K here, you have a link here. So you have a group element here. So the state is a function of a group element here. Okay? The state lives in a in a Hilbert space of functions of the group element here. Now, if you evaluate on the identity whether there was a function of HL or it's irrelevant. So the evaluation of the spin network with this link, or the evaluation of the spin network with intertwiner with intertwiner K is the same thing. But as a state, they're not the same thing. Because the state with a 4-valent intertwiner does not depend on a group element in between. While the state with 2 trivalent things does depend on the... And if you think physically, it's just... Let's put it naively. You have 1 point or 2 points. If you have 1 point, there is nothing to go from one to another, so the state does not depend on a group element. If you have 2 points, there is some degree of freedom of how you go from one to the other. So you have more variables around. Good. So that was first question. Second question is about G. First of all, let me give the formula, and then, of course, I'm not sure I remember the formula. It's delta m minus n times minus 1 to the j minus m. If it's not this one, it's almost, check it on the book. And then let me tell you what it is, because this is on Landau, actually. He computed. It's all over if you find it, but it's nice. So what it is, we have this representation spaces AJ. This is a representation of spin J theory. So the vectors there have an index m. The usual sort of the quantum mechanical notation is this one, right? It's the eigenstate of Lz. So they're objects which have a total spin J and angular momentum m. And then if you fix J and value m, so if you take a generic vector sum over m Vm Jm, this is a linear space, and this is this thing here. Now on this thing, there are two quadratic operations that you can do. There are 2 ways you can map this times across itself into the complex numbers. And the 2 should not be confused. That's the key point, which is, I already said that for spin 1/2, but this is general. One is that this is actually a Hilbert space. The matrices that transform this into one or the other are unitary with respect to a Hilbert product, a scalar product. So there's a scalar product. So there is a map from this times itself into the complex number, which is a scalar product. Okay? And how is this map? Well, this is a basis, and it is an orthonormal basis of this base diagonalized self-adjoint operator. So obviously, Jm prime is delta m prime. So that's a scalar product. And Vm, if you have Vw, this is Vm Wn delta Mn, but just using that. But remember, the scalar product is antilinear, so a bar, which is relevant if you do 3-dimensional real spaces, vectors, but if you do complex things, you have to remember the bar. So this is one quadratic structure on AJ, but there's another one. That's the point. And this other one should not be confused with that one. And what is the other one? Well, just think about basics, angular momentum things. If you take the tensor product of something which itself, this is the sum of some h k, k going from j minus j to j plus j of k. And in particular, inside here, since it starts from j minus j, which is 0, there is a 0 thing. So this is h0 plus other stuff. And this H0 is just complex number. It's a trivial representation. So that means they're given two vectors. In the scalar product, you can decompose its scalar product in components. There's one component which is invariant under SU2. Okay? And you say, oh, it's a scalar product. No, it's not a scalar product because this is linear in both. It's not antilinear. So there should be something else, which is the you take some V, you take some W, and out of these two, you construct a quantity, GMN, which is linear, there's no bar here, such that this thing is VW, different notation than this one, is invariant under rotation. So there should be a two-dimensional matrix with indices, it's a square matrix, with indices in this vector space here, which is invariant. And there always is. And it's this one. Now, it's much easier to think about this in the... when I get confused, I always think about irreducible representation of SU2 as symmetrized tensor of fundamentals. Because now, if you think about symmetrized tensor, you can write Hj, the element of Hj, you can write them as spinors with 2j indices. All symmetric, right? This is just another basis for this one. So there should be a version of G in the form A1, A2j, B1, B2j, which is this in that basis. And that's obvious, because that's epsilon A1, B1, epsilon A2j, B2j, because epsilon is the only invariant thing under SU2. And this is completely is symmetric here, is symmetric here. So you symmetrize all the A indices, you symmetrize all the B indices, or if these are already symmetric, you just use this product here. So this is equal to this thing here. So this is obvious what it is. If you translate it, if you go from this basis to the other, which is not too hard, if you just sit down and you think about LZ, you see how to write these in terms of this. This translated into that. That's not how Landau does it. The way Landau does it is as a physicist. He says, well, if you have a state with Lz equal m, and you want to combine it with a state, another state, which is in the fundamental, Lz has only eigenvalue 0. So the only possibility of having, say, a particle with angular momentum minus j together with something that gives angular momentum z is to put together with something with the opposite angular momentum. So this duality things should not take m with m, but m. So this should not be equal, but should have opposite sign. That's what it says here. And then he does a little calculation and discover that this is right up to a minus sign. In fact, put the minus sign. Yeah, it's a Landau way of doing things. Okay, so this is this object here. Okay. So we have this. So by keeping this duality here, which is the SU2 duality, is not the scalar product duality in mind, one can also use this as we use vectors. So keep the indices always up and lower with this. So to do invariant things by keeping indices up and down correctly. Using that notation, the 4-valent intertwiner, remember that the 3-valent intertwiner, M1, M2, M3, which is also the notation of J1, J2, J3, M1, M2, M3 is the same thing. this notation here. When this is the notation of the 3 J Wigner symbols. Then the basis of 4 valent intertwiners, M1, M2, M3, M4. So now it's not unique, but I can label this a basis of this with a spin K, where K is a range of all possible spins that have consistent Clebsch-Gordan condition with all of this. And this is defined to be, let me now be precise, J1, J2, K, M1, M2, M, G, M, N, K, J3, J4, N, M3, M4. Okay, well, everything is clean. Which it's obvious, right? You have 1 trivalent, 1 trivalent, and here you have to dualize. You have to put them together in an invariant manner. So it's not a scalar product here. It's this G here. It's an invariant way of combining things, which is something I used to do wrong at the beginning. I put the scalar product there, and then things were not working, and I couldn't understand. Okay. Now answering question 3 is completely easy, because what is the relation between this object here and the Clebsch-Gordan coefficient? They're exactly the same thing up to G. So these things are, if you put the indices up and down, you can think of this as M1, M2, M3, and the Clebsch-Gordan coefficients are M1, M2, M3, M. So the actual relation between the two is that J1, J2, J3, M1, M2, M3 is the Clebsch-Gordan coefficient J2, M2, J3, M3, J3, M, but this M and this M here are related by a G, M3, M. So they are the Clebsch-Gordan coefficients up to a sign and a shift of sign of the M.
So you can see that with something contracted with the Clebsch-Gordan.
Exactly. Exactly.
Clebsch-Gordan evaluated on.
Exactly. Exactly. All these things are, there are books in which all things are carefully written down. Typically they're written for atomic physics and nuclear physics, where they work with SU2 representation theory. There's a big book written by 3 Russians, which have all the 3J, 6J, NJ, and in fact, for some calculation loop quantum gravity, somebody has gone down and used them heavily. Okay, so that's 3. 4 and 5, I'll just say a few words. What fixes the little number here? Well, I anticipate that the little number here is going to be 8 pi, only because in front of the action is not 1 over g, but is actually 1 over 16 pi g, which is 1/2. The usual 1/2 in front of the action, because you have 2 things when you take derivative, and then there's 8 pi g, so it's an 8 pi here. But it's not just 8 pi, there is another number, which is called gamma, which is the Barbero Mirzi parameter, which will play a role in the following. And how does one derive the value here? By doing the canonical analysis precisely, and by requiring a la Dirac that the commutator are defined to be I H bar Poisson bracket. So you compute the Poisson bracket between variables. You demand that the quantum operators satisfy that. Now, why Dirac demands that? Because if this is true, then from the quantum theory, when you get the classical limit, you get the theory correct. So it's a backward. So I'll sketch the derivation, the canonical derivation. So the symplectic structure, the Poisson bracket. I'll sketch it, and I'll tell you when we do the action next week how this gamma come in. So last thing, what is this H? Now I said roughly that it's a rotation when you go to the frame of one tetrahedron to the frame of the other tetrahedron. This is correct, but it's incomplete. To see what exactly is the best is, again, do the Hamiltonian analysis carefully, and find the right interpretation of this connection here. And what we will find is it is the holonomy, the exponentiation of the connection along a line. That's the way you can think about it. But it's not the three-dimensional connection. It's not the spin connection. It's not the connection of the triad. Is the Ashika connection. And it has to be so because we have the operators L, E, and these operators here. They don't commute. So this is like position and momentum. So this has to be the time derivative of the other one. And the three-dimensional, as somebody was saying yesterday, if I have the three geometry, then the connection is uniquely determined, up to gauges. So if this was a spin connection defined by the triad, it would be a function of this, and it would commute with this. But it doesn't. I mean, this is a derivative operator, takes a derivative of that. So it has to be, or it has to at least to contain a part which does commute, which is the momentum, which is the time derivative. And in fact, it is a time derivative. We'll see. This is sort of the Ashika connection is a spin connection plus something which is essentially a time derivative of the metric, how the metric changes. So this will become clear ahead, but just wanted to anticipate to avoid that you two sort of get fixed in some idea which is wrong. So this is an holonomy of a three-dimensional connection, of an SU2 connection, but it's not the one uniquely determined by the triad, the Ashika connection, which knows about the time derivative of the triad, so the independent variable. So these were the answer to the all questions. So fixed some holes here and there. I hope this clarifies a little bit more this part. Do you have further questions? No? So let's keep this short, stop now, and start 5 minutes before 10, and we'll talk about time now. Just change and leave this on the side.